Let's first prove that if two operators commute, here's a theorem. If two operators commute, then they can have, well, let's prove something else first. If two operators have a common set of eigenfunctions, okay, then they commute. This is an easier thing to prove. And then we can prove the other one also. So let's say F1, F2, and so on is a common set, so that A hat F1 gives you back a constant A sub I, A1, A sub I, A hat F sub I gives you back a constant A sub I times F sub I. So this says that the functions are eigenfunctions of the A operator. The eigenvalues are A sub I. And we're also going to say that B hat F sub I is equal to some other constant B sub I, F sub I. So the F sub i's are a common set of eigenfunctions for operators A and B. Okay? How do we prove that they commute? How do you prove that two operators commute? Then you have to prove that A hat, B hat, operating on any function, let's call that function G. G is any arbitrary function, must be equal to 0, right? That's what commuting means. So we have to prove that. So how can we prove that? Well, the F sub I form a complete set, right? So we can substitute, we can expand G in terms of F sub I. So we can say A hat, B hat, and instead of G sub I, I'm going to replace that by C1 F1 plus C2 F2 plus C3 F3 and so on. Remember, we postulated the eigenfunctions of a Hermitian operator form a complete set, right? So that's going to be equal to 0. Can you prove that that's equal to 0? That's going to be 1. This is A. That's going to be A hat, B hat, okay, G minus B hat, A hat, G, right? So that's just going to be A hat, B hat, C1 F1 plus C2 F2 and so on, minus B hat, A hat, and then that's going to be C1 F1 plus C2 F2 and so on. Is that equal to 0? You can distribute, right? So that's going to be A hat, and then I can pull out my constant, right? So this is going to be C1 B hat F1, right? Plus A hat C2 B hat F2, right? Plus and so on, minus over here, I'm going to have B hat, and then I can pull out my constant, so C1 A hat F1, right? Plus C2 A hat F2, plus and so on. So what do I get here? I can pull out my C also, right? So that's C1 A hat B hat F1 plus, and over here minus, I can pull out my constant C1 B hat A hat F1 plus and so on, right? But this B hat F1, B1 F1, right? A hat operating on that, C1 plus minus, what do I have here? C1 B hat, what's A hat F operating on F1? A1 F1 plus and so on, And what do I have here? I can pull out my B1. It's a constant, so it's going to be C1, B1. What is A hat F1? A1, F1. Okay. Minus, what's this one? I can pull out A1, right? And what do I have here? B1, F1. B hat operating on F1 gives you B1, F1. And what do you get? This is the same thing as that one. That cancels out. And you can see all the other terms are going to cancel out as well. So the whole thing is going to be equal to 0. Okay? Now, a common proof you might find in some textbooks is they don't do this expansion right here. They just pick one eigenfunction and show that these two are equal, and they say, so they say, let's say that A, B, G equals BGA. Basically, they can show that BAG. You can show that if G is an eigenfunction, and then they're just going to say that, and then it must be that AB is equal to BA. Okay. If G is a specific function, then this does not follow. Okay. G must be an arbitrary function. In some textbooks, the proof is given where G is an eigenfunction right away. But so that doesn't follow. This doesn't follow because just because this operator operating on G is equal to this operator operating G doesn't mean that BA and AB and BA is the same. For example, if I say if this operator was d by dx, and this operator is d squared by dx, okay? If I operate that on e to the x and operate that on e to the x, they're equal, right? But that doesn't mean the two operators are the same. Okay? So this is actually a wrong proof. Okay. So anyway, so that's now you've seen that if they have a common set of eigenfunctions, then they commute. You can also prove that if they commute, then they can have a common set of eigenfunctions. That's a separate proof. Okay. So let's prove that statement right there. If they commute, then they have a common set of eigenfunctions. What do? We are going to assume that A hat, B hat, G, where G is any arbitrary function, right, must be equal to B hat, A hat, G, right? That's what we're saying they commute. Okay. Now, let's say F1, F2, F3 is an eigenfunction of A. It's an eigenbasis for A. Operator A. So you're going to say A1, F1 equals A1, F1, right? Oops. So what? So if I were to do A hat, B hat, F1, okay? Actually, let me do B hat, A hat, F1. What are we trying to prove? We already know that they commute, right? We're assuming that they commute. We're saying that we can show that, what are we trying to show? That we can show that B hat F1 would be some other constant, B sub I times B1 times F1, right? That's what we need to show. So we assume that's the case, then we need to show that if they commute. Okay? So how are we going to do that? Let's do B hat, A hat, F1. That's going to be equal to B hat, A1, F1, right? But that's also equal to, this is also equal to A hat, B hat, F1, correct? Because A and B commute. I know that, right? You still with me? Okay, now I can move my A1 up front here, so I can say that this thing right here, A hat, B hat, F1 is equal to A1, B hat, F1. Can you see that? This is, let's call this G, and let's call that G. So G is really B hat F1, right? So what do you say? What can you say about G? G is just another function. It's an eigenfunction of A, right? A applied on G gives you back G times a constant. So in other words, what we're saying is, what we're saying is that B hat F1 and F1, okay? B hat F1 is G, right? B hat F1 and F1 are eigenfunctions of A. In fact, degenerate eigenfunctions of A, right? Operator A. Actually, or they could be the same eigenfunction, right? So they're eigenfunctions of A. Let me just make that. Let's just say they're eigenfunctions, both eigenfunctions of A with the same eigenvalue. But what did we prove last time about Hermitian operators? Non-degenerate eigenfunctions are not linearly independent, right? So what that suggests then is that B1, F1, this thing which we call G, is just a constant times F1. So, right? So, in other words, we say G and F1 are not linearly independent. So, in other words, you can write G as just some constant times F1. So, what we just did here is we've proven that B hat operating on F1 gives you back another constant times F1. And this constant, we can call that B1 if you want.
So they're
not linearly independent. Okay? So that means it's possible for us to choose a common complete set of eigenfunctions for two operators if they commute. And if we can do that, remember, if your wave function, your psi is an eigenfunction of an operator, you can precisely determine that property of that operator, corresponding to that operator. Now, what if level A1, this eigenvalue A1 is degenerate? If there's more than one possible linearly independent functions of eigenfunctions of A with this eigenvalue, then you're going to have to write. B1, F1 as a linear combination of the eigenfunctions of A. But it's always possible, we've seen that with the Schmidt orthogonalization procedure, that to select among all possible degenerate eigenfunctions, it's possible to select a common set for a set for your particular, what's the word? It's possible to select from those functions. You'd be able to show it's possible to select from those functions a common set. So not every one of these is going to be an eigenfunction of B, okay? But it's possible to select one of these particular linear combinations as also an eigenfunction of B, and you can make that as part of the common set, okay?